Hello everyone. Let us continue learning C language. In our previous video, we discussed about how data types are used in C language and what are the primitive data types that are available in C language. And those data types are character, integer, float, and double. And we also discussed about modifiers. We talked about two majorly used modifiers, and those are sign modifiers and size modifiers, signed and unsigned modifiers, and short and long modifiers. And we also talked about how it is being used in Turbo C and GCC compilers individually. Now, in this video, we'll discuss about how a memory is being allocated for a variable for any data type for that matter, and how the data is being stored and retrieved from the memory. We all know that in terms of computer, the memory is always binary, that is ones and zeros. Now, let us see how an integer value is stored inside a memory and being retrieved and being printed out. Yes, let's get started. Let us talk about a common short integer variable in terms of a GCC compiler. I'm declaring a short int with the name of n, and I'm assigning a value of 9 in it. Yes. Now we all know the size of short integer in terms of GCC compiler is, yes, exactly 2 bytes. It's 2 bytes, which means it is 16-bit data. It is 16 bits. Okay. I'm going to mention, or I'm going to denote each and every bit as a hyphen. 1, 2, 3, 4, 5, 6, 7, and 8. So this is 1 byte for me. And this is going to be my second byte. And this is the memory that is being allocated for my integer, which is named as n. Okay. Now, how this value will be stored inside the memory? Whenever we provide a decimal number, that is 9 is a decimal number here. So when I provide a decimal number like this decimal number will be converted to its equivalent binary. The equivalent binary of 9 is nothing but 1001, which is the binary of number 9. Now this data has got 4 digits in it. As you could see, it is 1001. It has got 4 digits, and these 4 digits will be stored in the rightmost places. In these rightmost places of 4 bits will be stored as 1001 in the last 4 places. Now what will be stored in the remaining 12 bits? These 12 places will be filled with zeros exactly. Okay, and this is how a number, a decimal value, is stored inside a memory and is being retrieved and being printed. Yes, as you could clearly see here, the space for an integer variable in terms of a C language is limited. It is limited to 16 bits in terms of a short integer. If this is going to be a long integer, for suppose long int n is equal to 9, then you very well know that the size is going to be 4 bytes. So which means you'll have 32 bits. Yeah. So it will be stored as my 4 bytes are this data, and the number 9 will be stored in a 1001 in this format. Yeah, I hope this is clear. Yes. Now, as you could very well see here, the memory is absolutely restricted. It is only limited to 16 bits or 32 bits based upon the data type you are specifying it here. In that context, the value range for each and every data type is also restricted. In case for a short integer. Okay, I'm going to talk about a short integer. Yes, for a short integer, the memory we are giving to a short integer is 16 bits. Each bit can store only a 0 or 1. So which means it has got 2 choices. Okay, it has got 2 choices. It's going to be either 0 or 1. In that case, I can store 2 to the power of 16 different values. I can store 2 to the power of 16 different values, which means I can store 65536, which is the value of 2 power 16. I can store 65,536 different types of values inside an integer variable, which is a short integer. Okay. Now all these data looks a bit of clumsy. It is very hard for us to handle. Reason because we are talking about a huge space of memory to work with. Okay. Now for that sake, for the sake of understanding, for the sake of simplification, okay, I suggest we guys learn with a smaller data type. Okay, a smaller memory. I'm going to assume, okay, I'm going to think about a compiler. I'm going to think about a scenario where my integer variable called a is allocated only with a 4-bit memory. Okay, I'm going to allocate this variable with a with the 4 bits memory. Okay, my memory is going to be only 4 bits, and this assumption is purely for the sake of understanding. This has nothing to do with the actual C compiler, which is either Turbo C or GCC compiler. Okay, please mind this. In this context, I have got 4 bits. I have got 4 bits here. Each bit can either store 0 or 1. In that case, I can store, as I told you earlier, we can store different values, and those different values are, I can store 0, 0, 0, 0 in all bits, or I can store 0, 0, 0, 1 in the first bit, or 0, 0, 1, 0. Okay, let's quickly run through this. So this is the first set of values. Let us continue further. And that value, I wish to write it on the right side of it, so that I'll tell you why it is. So these are the 16 different values which we can store inside a 4-bit memory. As I told you, it's a 4-bit memory, and each bit has got 2 choices, 0 or 1. So I can store 2 power 4 different values. 2 power 4 instead means 16 different values. 16 different values, and these are exactly those 16 different values. Now, in terms of decimal, okay, all these are binary. Let's convert this into a decimal equivalent. Okay, the decimal equivalent of this number is, okay, the decimal equivalent of this number is 0. This is 1. This is 2. This is 3. Now let's again quickly run through this. Yes, so these are the values exactly. 0 to 15. I can store values from 0 to 15. Can you understand this? So this is pretty much perfect. Now, as you could literally see, all the values here are only positive values. It has only plus sign in it. Yeah. So this range, what I've described here, which is 0 to 15, is basically an unsigned range because there is no sign that is being involved. If there is a bit which I have to use it for sign bit, okay, which bit will be used for sign bit? And obviously we know it's going to be the leftmost significant bit, which is called as LSB. That is the bit which will be used for your sign bit, and that bit is exactly this position, okay, this place. As you can see on the screen right now, this highlighted part, that bit is going to be your sign bit. And whenever I have 1 in it, if I have 0 in it, it's going to be a positive number. When I have 1 in it, that will be represented as a negative number. Okay. In that case, the numbers which I have written on the right hand side of the screen, all these data are going to be your negative numbers, which is going to be your minus sign numbers. Okay. In that case, how these numbers, what are the equivalent values? What are the equivalent negative values for these numbers? How am I going to find it? Okay. Now let's talk about this point, the last number in it. When I want to add 1 to this number, that is this number, whatever we have on the screen right now, 1, 1, 1, 1. When I want to add 1 to this number, when I want to add 1, okay, when I want to add it, what is the answer we are going to expect? How this is going to be added? Okay. Now for this, the answer is going to be 1, 0, 0, 0, 0. Am I right here? Is this the value which you could expect? Addition of 1 to all 4 ones, your binary addition basically. Okay. Now in this context, this equivalent, this number is considered to be 16. Yeah, this equal number is considered to be the binary of 16. But when it comes to storing this number in our binary system, which is what we have right now, the 4-bit system. Okay, I cannot store 5 bits. Reason because my memory itself has only got 4 bits. Okay, so what it does is nothing but it takes up only the last 4 bits. It takes up only last 4 bits and stores it in the place of 16. Even if I want to try storing 16 in the memory, it stores only last 4 bits. So thus that is in turn called as 16. So it might be 16 what we are trying storing here, but it won't store 16. The equivalent value that is stored instead of 16 is 0. It won't store 16. Instead, it stores only 0. Reason because this one, the one you have here, is basically an overflow. This one is basically your overflow data. Can you understand this? Yeah. So this is what is called as an overflow scenario here. Okay. Fine. Now, this is a reason why we say that the data types in C language are in cyclic order. It's going to be in the cyclic arrangement. They are stored in a cyclic order. Okay. After 15, it is going to be 16, which is basically 0. Clear. So when you could see this in a number line, after 15 is going to be 16. So after 0, that is before 0, in a negative number, before 0, in a number line, on a negative number line, what is the number that is present before 0? Which is literally your -1 data. So it's called -1. And before -1, it is -2. Before -2, it is -3. Before -3, it is -4. Before -4, it is -5, -6, -7, -8, and so on and so forth. Can you follow this? Okay. And in terms of, so if it's going to be a signed range, okay, unsigned, I told you it is 0 to 15. It is going to be an unsigned range. If it is going to be a signed range, it is going to be -8 to +7. So this is will be yours. So this will be your signed range. Okay. Is this clear for everybody? Let's continue further. Okay. Now taking this into consideration, okay, this range, taking this range into consideration, taking this range into consideration, so this is the range we talked about in terms of your 4-bit data. Fine. Now taking this into consideration, let us understand how things work with your actual 16-bit data. Yes, our actual integers, which is of 16-bit data. Okay. Our short integer, the short integer we have has 16 bits. And this number what we had has got only 4 bits. Okay. So this assumption what we made has got 4 bits in it. And the actual short integer what we have got contains 16 bits. Okay. Since it has got 4 bits, the range starts from, for unsigned, the range starts from 0 to 2 to the power of 4 minus 1, because 15 can be represented as 2 power 4 minus 1. For signed, it is -2 power 3 to 2 power 3 minus 1. 2 power 3 whole minus 1 for signed. You understand this part? So if this is going to be a 16-bit range, okay, for unsigned, the range is going to be 0 to 2 power 16 minus 1. So it's going to be 0 to 65535. For signed, it is going to be -2 power 15 to 2 power 15 minus 1. So it's going to be -32768 plus 32767. So this is the range what we are expecting here for a short integer variable. Are we clear with this? Hope this is good. Let's quickly try and execute and verify this data. Now let us declare a short integer variable. Let us delete our previously existing data and start with a short integer. And I'm naming the variable as n. Yes. And I'm storing a value of 32767 in it, which we earlier talked about. This is the highermost data that can be stored inside a short integer. Hope you remember that. And this line alias can be also written as short n is equal to 32767. Okay, even this is accepted. The need of writing int is not necessary because I have mentioned short already. Now, what I'm going to do is nothing but I'm going to increment the value of n by one value, that is n plus plus, which says n is equal to n plus 1. I'm incrementing the value of n by one value. Okay. Now I'll print the data. Printf %d, comma, n. I'm just literally printing the value of n. Now let us say I'm going to compile this file again. I'll run it. Now what is the output you are seeing here? We are not getting plus 32768, rather we are getting minus 32768. You remember it? Reason because I told you the range of short integer is from minus 32768 to 32767. So I've assigned the highermost positive number for the number. And when I add 1 to that number, the number becomes cyclic. We know that the number system in data in C language are cyclic. So after plus 32767, it is going to be minus 32768. So when I increment by one value, it becomes minus 32768. And that is a very evident proof that the numbers are cyclic in order. Hope you understood this. And the same thing, let us see what happens in our unsigned integers. Okay, I'm going to call this as unsigned shortened. Now I'll compile this again. Now you could see the values plus 32768. Okay. Now let us go to the highermost range of unsigned integer, which is 65535. Okay. Again, I'm incrementing n by one value. I'll compile this again. I'll run it up. You could see the value 0. It is supposed to be 65536. Yes, the next number. But since that is the highermost limit and the number becomes cyclic after that point, and this becomes 0 net. Okay. I hope how the numbers are cyclically stored in C language. I hope things are clear as of now. Yes. Now let us try to extend this. Let us talk about the overflow conditions here. Okay. Now in a short integer, yes, I'm going to store a number which is beyond this range because we know the range is only from 0 to 65536. Now let me talk about storing a value which is of range 1 lakh. Okay. I'm going to store 1 lakh in it. So there is no need of incrementation to be happening here. So I'm removing the incrementation part. Rather, I'm going to print only the value, which is an unsigned short integer. Now let me compile this and show you that overflow warning. I'll clear the screen as of now. I'll compile this. Now look at this part. We are clearly noticing a warning statement here. Okay, we are clearly noticing a warning statement that is exactly on the third line where we have written unsigned short integer n is equal to 1 lakh. And that is a value which is out of the range. You could see this warning statement. Unsigned conversion from int to short unsigned integer changes value from 1 lakh to 34464. So it is not storing 1 lakh, which is supposed to store. Rather, it has stored only 34464, which is an altered number. When I run this file now, you could literally see the output is not 1 lakh. It is going to store only 34464. Yes. I hope you understood this. Now let's talk about the same scenario in terms of your signed short integer. Okay. I'm going to remove this part of unsigned short integer. I'm going to make this as signed short integer. Again, I'll compile it. Even this time, we are expecting a warning statement. But let us see what is the change in the warning statement as of now. Do you notice any change in the warning statement as of now? Yes, obviously, the value is not 34464. It is minus 31072. Why is that so? The reason because 34464 will not fall under the range of short integer. Reason because signed short integer ranges only from minus 32768 to 32767. Exactly. And that is why this number of 34464 is not being said. Rather, that number is again being converted into minus 31072. Now, we all need to understand how 1 lakh has become such a number, which is completely vague and we have no clue about how that number is being made. Okay. Now let's try to drill down a bit and understand how this number is being achieved. Okay. Now for that sake, again, we'll get back to the same scenario where we assumed a 4-bit data. Okay. Now earlier in our video, we talked about a 4-bit data and assumed a memory where we used 4 bits to store an integer variable. Now let me talk about the same scenario. I'm going to talk about a variable called a, which needs to store, which is a signed value basically. Okay, so I'll make this as signed, which is a signed variable. I'm going to store a number a with a value of 13 in it. Okay, the binary of 13 here is nothing but 1101. That is a binary of 13, but this is signed. Okay, now how a compiler treats this memory, how a compiler deals with this kind of a value. Okay, now what a compiler will do, because we are assuming a 4-bit memory, compiler comes ready with 4 bits. Okay, now the first thing what it does is it starts storing this data in the memory. So it starts from the rightmost point, 1 0 1 1, and this is how compiler stores it. It starts storing from the rightmost place, rightmost bit. Okay, after storing it, when I want to retrieve it, when I want to print it, when I say printf %d comma a, when I want to print it, that is when it sees this data called signed. If the sign modifier says signed, it goes back, checks the LSB. Since it is 1, the output is going to be a negative number, so it prints a minus sign and converts this whole data, that is the remaining data, into its equivalent binary value. So it's equivalent binary value for 13. We all know the binary of 15 is -1, 14 is -2, 13 is -3. Yes, so it prints -3 in that place. Okay, it prints -3. Clear? Now, how this data 13 has become -3? Now, this in case of a 4-bit memory, we can understand this. Now, let us talk about another value. In the same 4-bit memory, I'm going to talk about a number that is int a is equal to 93. Now, we all know binary of 93. What is the binary of 93? Let's check it. So, in my calculator, we have this option called as a programmer's calculator. Yes, which can be achieved from this window. You can say programmer's calculator. So in the decimal value, I'm going to say 93. The equivalent binary of 93 is 1011101. Okay, it says the binary of 93 is 1011101. Okay, it has got 7 bits in it, but my memory is restricted only to 4 bits. So it stores only the last 4 bits. So when I store 93, in the memory, it stores only 1011. So when I want to print it, while storing, I might have stored 93. But when I want to print it, it prints only -3. Reason because this is going to be a signed integer. Okay, it prints -3. If this is going to be an unsigned integer, this would have printed 13 for me. Okay, now we need to know how the number is being achieved, because for a 4-bit memory, storing it, visualizing it is much easier. But this cannot be done for 16 bits because the size is very huge. Now, how I can formulate it? Okay, the formula is pretty simple. In a 4-bit memory, how many different values we can store? I told you this already. In a 4-bit memory, how many different values we can store? We can store 2 power 4 different values, and that is 16 different values. Okay, a number like 93, which is not in the range of a signed integer. Signed int ranges from -8 to +7. Number 93 is not within the range, so subtract 16 from it. 93 minus 16, what is the answer we get? So 8 and 13. So we have got 7 and we have got 77. Okay, again 77 is not within the range. Again subtract 16 from it. Again minus. So when I subtract it, this is going to be 6 and this is going to be 17. So it is going to be 9 times. So it's going to be 1 and 5. So 61. Again subtract 16 from it. Minus. So 61 minus 16. So this is going to be 5 and 11. So this is 5, 45. Again subtract 16 from it. So it's going to be 3, 15. So it is 9 times 29. Again from 29 subtract 16 from it. Again do it subtraction. So it's going to be 13. Now this 13 is not within the range of signed. So again subtract 16 from it. That is when you get -3 as a number. You understood this process? Yes. Very good. Now for unsigned range, if this is going to be your unsigned integer, the range is from 0 to 15. So in that context, the process ends one step ahead of this, because 13 itself is a point where I achieve the range part. So that is why when I store a number which is beyond this range of 93, I'm getting 13 if this is unsigned, and I'm getting -3 if it is signed, and I'm subtracting 16 from it because this is a 4-bit data. Let us continue the same. Let us extract the ideas from this. If I'm going to do this part, if I'm going to extend this part for 16 bits memory, so I can store 2 power 16 different values. 2 power 16 different values corresponds to 65536. So this is the number that I had to subtract. 1 lakh is a number which is beyond this range. And if this is going to be unsigned integer, the range is from 0 to 65535. If this is going to be signed integer, the range is from -3 to 76768 to 32767. When I subtract out of it, I have to subtract by 65536. So this all becomes 9, and this becomes 10. So it is 4, 6. So 34464 is the number. Okay, hope this is clear. It is 34464. Again, if this number is not satisfied, what I have to do? Again, I have to subtract, because this falls inside the unsigned range. This not comes under the signed range. So what I have to do? I have to again subtract it. Again, I have to subtract it by 65536. So the answer result I would get is -310. So this is the number I would get. And that is why in terms of signed range, it is -31072 in terms of signed. In terms of unsigned, it is 34464. I hope you understood these details. And this is exactly the same way how the data is being used for long integers as well. And as we know, the long integer uses a 4-byte memory for a long integer, that is a native int data type in GCC compiler, which we already discussed. In terms of long integer, the variable ranges from, we have got 4 bytes of data, which means we can have 32 bits. The range is from -2 power 31 to 2 power 31 minus 1 for a signed long integer. For an unsigned long integer, the range is from 0 to 2 power 32 minus 1. So these are the corresponding ranges. Now we all have a question, right? In terms of integer, this is perfectly okay, but what if in terms of a character? Okay, now for a character variable, okay, let's talk about the same scenario for a character variable. Character ch, this variable called ch has got 1 byte data, and that means it has got only 8 bits. So the value ranges from 0 to 2 to the power of 8 minus 1 if this is unsigned, and it can store -2 power 7 to 2 power 7 minus 1 if this is signed. In terms of value, I can call this as 0 to 255 if it is unsigned. If it is going to be signed, it is going to be -128 to +127 if this is going to be signed. Now we all know that character variable stores only character, but what we are talking about are decimals here. We are talking about some decimal numbers. How this is possible? This is when we have to understand the way a variable that is being stored, that is a character being stored, is with the help of ASCII table, which is a common standard code for each and every character that we could press possibly from the keyboard, right? All the keys from the keyboard, including your enter, including your tab space, including your space, even your punctuations, dot, comma, and any other key from the keyboard always has a certain decimal value as its unique ASCII value. Now, in order to understand much more in detail about these unique ASCII values, let us talk about few of the other characters. Now, we all know when it comes to characters, we have both lowercase and uppercase characters. For example, we have alphabet A both in lowercase as well as in uppercase. Now, in our coding window, let's talk about a character variable called ch, and let us store our character variable A, a capital A, and print its value, but not as %C. We'll print it as %D to understand what is the ASCII value that is for capital A. And let's end with the return 0 statement. Now let's compile it and let's run it. Okay, so I'll print this character as 2 formats. I'll print %C and %D. So I'll print ch twice. Okay, Now let me run this. So capital A is 65. Let me try for small a. Compile and run again. So small a is 97. And let's try for a character as 0. 0 is not as a value, but as a character. And for 0, it is 48. And let's try for a new line character, that is /n, which is supposed to be 10. Now see how it prints. Okay, here you could see previously it was printing the character and then the number. Yeah, that is how it was printing earlier. But here you could see there is nothing being printed on this line, and it is directly came to the next line. You could see 2 lines here because it has literally printed /n, a new line character. So that is why I'm not seeing /n here. Rather, it has come to the next line. But when it is /t, okay, it is a tab space. I'll compile and run it. You could see 9 is printed a bit 1 tab space from the leftmost point of the screen because it is /t that is literally printed here. And I hope this is clear. Well and good. Let's proceed in further and let's talk about the value range of a character variable. Now for character variable, we all know the range is from, if it is going to be unsigned, if the range is from 0 to 255. If this is signed, the range is from -128 to 127. Yeah. Now let me store a value in it and let me call this as value as 300. Now let me print only the decimal part of it. Let me print only in the decimal format. Okay. I'll compile it. Now you could see very well there is a warning here literally. Reason because the range is only from 0 to 255 and 300 is way beyond the range. And obviously there is existing an overflow statement here. And how this overflow is being handled is pretty much simple here. 300 is a number which is not in the range. So what it does is nothing but the value of 256 is separated from the value of 300, and the resulting what you are getting is 44. 256 is subtracted from the value of 300, and because 256 is being separated, reason because I have got 8 bits. I can have 2 to the power of 8 different values, and 2 power 8 value is nothing but 256, and that is why we are subtracting 256 from it. And what we are performing here, okay, on this place, we are trying to convert an integer value into a character. So this literally in terms of C language is called as typecasting. And there are 2 types of typecasting that exist in C language, and those are explicit typecasting and implicit typecasting. In our next video, we'll discuss much in detail about typecasting. Until then, see you.